this demonstration, you'll learn some tips on how to obtain a converged solution for a fluid flow simulation. I'll import a journal file that will read in the geometry containing multiple inlets. This script contains all the necessary settings required to solve the physics. In fact, you can see that your physics is up to date. After solving the physics, you will need to check whether or not your solution is converged. There are a number of ways to find out if convergence has been achieved. You can look in the Messages tab. If convergence has not been achieved, you will see a message to that effect. In the case of a converged solution, you will not see a message. You can also check for convergence in the Solution Quality tab. Here you will see a plot of the residuals at each iteration. To gauge whether your solution is converging, you'd want to see the residuals for all the equations except turbulence, which are excluded from the convergence criteria check, drop below 1 × 10⁻⁵. There will be cases where your solution does not converge. Let's run through some typical scenarios where convergence isn't obtained, and we'll provide you with some tips on how to achieve convergence. This first case shows residuals decreasing, but not reaching the target convergence criteria of 1 × 10⁻⁵. In addition, in the Transcript tab, it states that the solution is not converged. Let's increase the maximum number of iterations in the Solution Controls panel to 1000. We'll update the solution and check the residual plots. This should result in a converged solution, and we can confirm this in the Transcript tab. This second case displays residuals of slow convergence. You can see that the solution finally converges after 789 iterations. To speed up convergence, let's try increasing the time step scaling factor to 10. This setting is found in the Numerical Controls panel, and under Solution Control, expand Advancement Control and Flow Control, and under Flow Pseudo-Transient, enter the time step scaling factor. Don't forget to update the solution. Choosing a scaling factor larger than 1 can often accelerate convergence, particularly if the convergence plots show smooth behavior, as in this case. Here you can see that it converged in only 78 iterations. Sometimes the solution does not converge for other reasons. For example, we will decrease the maximum face size in the meshing task to 0.08 to better resolve flow features. We'll update the mesh and solve the physics. With this mesh, the Solution Quality tab shows oscillating residuals. The Transcript tells us where the maximum residuals are located. We can create a point at one of those locations and inspect the mesh and solution in the vicinity of that point to check for potential issues. To create a point, let's navigate to the Results task page and go to Construction Geometry to add a point. Let's create a point using the coordinates of the maximum residuals. Next, we'll create a plane anywhere in the XY direction to display our plots. We're going to create a velocity vector plot and inspect the results where the maximum residual is located. Choose the location to be the plane that we just created and the variable to be velocity. We want to go back and remind ourselves where the location of the maximum residual lies, right here. And we'll zoom into this location. Here we can see a separation zone, which is likely to be unsteady. Unsteady flow cannot be captured with a steady simulation such as this, which is why the residuals do not converge. This concludes this demonstration of convergence tips for a fluid flow simulation.